Hello, this video is to demo the little program that I've been working on, tinkering on and off for a few months. And it is a program to perform regression analysis on arbitrary data using evolutionary algorithms and generation of abstract syntax trees. So I will not go into detail about this subject because I'm not an expert at them, but also because it's not interesting for this video. But essentially, what we're trying to do is, look at all these points and find the curve, find an equation that generates, that as closely as possible approximates this found data, and this a wide field. But what's interesting about this approach is that it can deal with very arbitrary data and find some equations that are quite complex and quite unintuitive. It doesn't have to be limited to linear regression or anything like that, because we generate these abstract syntax trees in our program, and they are very flexible in terms of expression. So yeah, it is good reading, of course. And what was most interesting about this program, I think, is the way I represent these abstract syntax trees in terms of evolutionary algorithms and genetic data. Yes, so the reason this is good is because, or this program could be interesting, is because it allows us to look at very arbitrary data and find equations that describe them. And normally, in my experience at least, you have to have some preconceived notion of how the data is structured in order to do regression analysis, and this program does not do that. So yes, in terms of how it actually works, I'm hoping to show you a little bit. So for example, if we have a set of input data here, I'm just hard coding it in now in the program. So for this input data of x equals 1, 2, 3 and 4, and y equals 2, 4, 6 and 0, and results equals 1, 2, 3, 4. Our program wants to find what, in terms of looking at these parameters, what generates this data, or what comes as close as possible to generating this data. And you might have noticed that this is a fairly simple equation. It's just result equals x. So we're expecting that our program will find that quite easily. So let's see what we get. Yes. So after like one iteration or something, it realized that, yeah, actually the second iteration, I guess, finds that x equals it's a perfect fitness. So lower fitness is good, because that means that it's closer to the distance is very low between the results and our generation, our equation running on the input data. So let's try something. Let's try a little more interesting, which could be, for example, result equals x plus, which could be, for example, x equals result equals x plus 2 times y. So that would be 1 plus 4, 2 plus 8, 3 plus 12, and 4. And let's run that instead, saving it, running it, and we expect that we will find this. So you find this is also a very simple equation, obviously. Y plus y plus x, which is the same as x plus 2y, of course. And these are simple equations, so I'll do one more simple, I guess. So maybe x squared. So let's do 1, let's do 4, let's do 9 and 16. And now we expect to find x times x or x squared, which are obviously equivalent. Yes, so it took, it said if you caught it, it took a few generations to find it exactly, but we ended up with x times x, which is same as x squared. Alright, now that we have some basic understanding about how the program works, we will try a little harder example. And we could just do it for any of our data. We could just enter it like this, hard code it and enter it. But to make things easier for us when we're testing, we can also, for some values of, if we're doing two variables, then for some values of x and y, we can just generate the data here, runtime, and put it in. So we will do like for 12 different values of x, and for each of those 12 different values of y, we will make some input data, and we will enter our results of the equation we want. And the solver doesn't know anything about this. It doesn't see this. It only sees the results. So it's not cheating, and it's not looking at this. So let's try a harder equation, something more exciting. And the example I had in mind was something like 3 times pow x to the power of 2, and we'll do minus 5 times y, and then plus 2, so we get x power of 2 and some y in there and some constant, and then we'll run it. And this will probably take a while, but I'll let it run and see how long it takes to get there. And it will use 12 times 12, so that's 144 values, and we'll see how long it takes. Alright, I return after like more than an hour, I think, and it looks like the equation has been solved. And you can look at this. If I pause it, you can look at this equation, and it's obviously it's not expressed as we would express it, and that's because there are a lot of different ways. Obviously you can express the same equation so that it's equivalent, but I can see on the fitness that it must be correct, and it looks correct to me. So I will use what I usually do when it's more complex than this is I take the equation and enter it into Wolfram Alpha, and then we'll get some sort of more human version of the equation. Blah blah blah. Can I get a simple version here somewhere? No. Alright, yeah, well, okay, we can look at this, and this looks fine to me, right? It's 3 times x, very similar, close to x, times x, which is this is very close to 3x squared, minus very close to 5y, plus very close to 2. And the longer I let this run, the closer you'll get. And this was our equation. So I'm satisfied with this result. And because of the fact that it is a genetic algorithm, the time it takes to converge varies a lot. But I could probably have stopped this a while ago, and it would have been okay. But it can take the same equation, the same set of data can take. Sometimes it takes twice as long as other times. It's because this random distribution of organisms, evolutionary organisms, it's a lot of variance. But yeah, hope you enjoyed this.